Okay, good morning, everyone. So today, do you hear me?
Yes, I can.
Okay, great. So today we are going to continue talking about exponential functions, and especially we want to introduce the number e, which is sometimes known as the Euler's number. It is also known as the Napier constant. So these are the names of two mathematicians. Leonhard Euler, he was a great mathematician, and also Napier. He's not as famous as Euler, of course. Okay, so let me share my screen with you. Not yet.
Yeah, she didn't respond by phone,
Okay.
so maybe she's coming.
Okay. Okay, so let us look at what we did yesterday. So we talked about the exponential functions like 2 to the power x or 3 to the power x. And you see there is a significant difference between 2 to the power x and x squared. Because when you have 2 to the power x, the exponent is a variable. The exponent is subject to change, right? But for x squared, the exponent is fixed, it's 2. But the base is changing, okay? Now, the value of this function at a few numbers, here you see in a table, so when x equal to 0, then f of x would be, no, sorry, it's not 0, it's 1. My mistake. So 2 to the power 0 is 1, right? So any number to the power 0 is 1. 2 to the power 1 is 2, 2 to the power 2, 2 squared is 4. When x is negative, then 2 to the power x is a number less than 1. Like x to 2 to the power negative 1 is 1/2. 2 to the power negative 2 is 1/4. 2 to the power negative 3 is 1/8, and so forth. So when x is less than, is a negative number, 2 to the power 4, 2 to the power x would be a number less than 1. Okay, and here is the graph. Now, let's do some transformation with this graph. If instead of 2 to the power x, you have like something like y equal to 2 times 2 to the power x, then there are two ways to look at this function. One can say that, okay, it's just a, I mean, there are two ways. We can say that it's a vertical stretch. So this guy is a vertical stretch. Right? So let's just draw them. So that is, so what is 2 to the power x? You remember, so at 0, the function is, the value of function is 1. So that means the y-intercept is 1. So it goes, and when x goes to minus infinity, it goes to 0. So it's something like this. Now, if you have a vertical stretch, you are going to get something like, because so the y-intercept would be 2 instead of 1. I mean, it's something like this, not exactly, but so this would be y equal to 2 to the power x, and this, the green one would be 2 times 2 to the power x. But there is also another way to look at this 2 times 2 to the power x. Any suggestion? Two times 2 to the power x, you have the same base. You have 2 and you have 2 to the power x. When you multiply two numbers with the same two exponents with the same base, what you can do? You just can add the exponents, right? Like, what is 2 to the power 3 times 2 to the power 4? It's 2 to the power 7, right? So 2 to the power 1 times 2 to the power x. This would be 2 to the power x plus 1. So one can say this is a horizontal transformation. Horizontal transformation, which is basically a shift, 1 unit shift, or 1 unit moving to the left. So moving or shifting 1 unit to the left. Okay, so you have something like this. This is your graph. Imagine this is the, and I first draw the 2 to the power x. 2 to the power x, as we see, it's something like, I mean, it grows faster. Now, if you shift it 1 unit, and this is this, imagine that this is x equal to 0. If you shift it 1 unit to the left, then what you get? Right? Is this picture clear?
Clear.
The green one is shifted 1. So you shift it 1 unit to the left. Okay. So you can do lots of things to this. So you can add 1, for instance. You can say 2 to the power x plus 1, or 2 to the power x plus 1 plus 1, or minus 1. So if you add something, you just have to transform it vertically along the y-axis. Depending, if you add something positive, you just move it up. If you subtract or add something negative, you move it down. Okay. So I expect you to know this type of transformations, but if you have any problem or questions, just let me know. There are lots of examples and pictures in the textbook. I want you to look at them. Okay. Okay. It is also good to look at the graph of 2 to the power minus x. Y equal to 2 to the power minus x. What is 2 to the power minus x? So there are two ways to look at this graph. One way, again, is to say that, okay, this is nothing but 1/2 to the power x. And work with this, right?
Mhm.
So I just first draw 2 to the power x, which is the original function. This is 1, so it passes through this. So for 2 to the, or you can say that because you switch x with negative x, it just goes, you just do a reflection along the y-axis, right? So this is y equal to 2 to the power x. The green one is y equal to 2 to the power negative x. Which is the same as 1/2 to the power x. So the lesson here is this. Whenever you have a number which is less than 1, if the base is less than 1, the base of an exponential function is less than 1, then the graph looks like the green graph. It's decreasing. If the base is less than 1. Why it is decreasing? Because when you take powers of a number less than 1, it's getting smaller, right? So for instance, look at 1/2. So what is the powers on 1/2? So if x is 1, 2, 3, 4, what are the powers of 1/2? 1/2 to the x. So it's 1/2, 1/4, 1/8, 1/16. You see?
Mhm.
So this is something known as a decreasing function. That means when the value of x increases, the value of y decreases. However, for 2 to the power x, it is an increasing function because when the value of x increases, the value of y increases too. Okay.
Mhm.
Okay, so the bottom line is that if the base is a number greater than 1, then you have an exponential function. The graph looks similar to 2 to the power x, the black one. If the base is a number less than 1, like 1/2, 1/3, the graph looks like the green graph. It's decreasing. And another difference is the behavior of these two guys at infinity. So 2 to the power negative x, when x goes to positive infinity, it goes to 0. You see?
Mhm.
Here, when x goes to positive infinity, the function goes to 0. But for 2 to the power x, when x goes to positive infinity, it goes to infinity. However, when x goes to negative infinity, then 2 to the power x goes to 0. Okay?
Mhm.
So let me write down these two important things. So the limit of limit of 2 to the power x when x goes to minus infinity, it is 0, which is equal to limit of 2 to the power minus x when x goes to plus infinity. 2 to the power minus x is 1/2 to the power x. and the limit of 2 to the power x, when x goes to infinity, it is infinity, which is the same of limit of 2 to the power x minus x when x goes to negative. Okay.
Mhm.
Okay, let's see. Okay, now is this clear? So 2 to the power x and 1/2 to the power x.
Mhm.
So here I just talk about 2, but it can be 3, 4, 10, any number can be the base, okay? The behavior is similar. But of course, the values of the function, depending on base, would be different. But the typical behavior, they have same characteristics, basically, okay? Any question?
No.
Okay, so let's talk about the number e. So this is also known as Euler's number. Or also known as Napier. I guess it's like this, constant. So it's the number we denote it, we use the symbol E to denote this number. First of all, it is an irrational number. So E is an irrational number. And its value, it's something between 2 and 3. So it's an irrational number between 2 and 3. It's like 2.7 something. Okay.
Mhm.
So now I said that the one question is where this number comes from. So one example comes from finance. So one can say that it's arising in some finance examples, which is compound interest. When you want to compute the compound interest, so that is example in finance. Which is compound interest. Do you know the meaning of interest in finance?
No.
Okay, so interest, let me give you some simple example.
Oh, I remember this. Got it. Sorry.
So that means, for instance, you have financial institutions like banks, okay?
Oh,
And
okay.
you have some savings, you put some money in savings into your account in a bank. And the bank, if you keep that money in your account, and if you don't touch it, then they give you interest. That means they give you some percent of your money back to you each year. So they add some percent of your money each year or each month, depending on your contract. Okay. Okay. So let me start with this. So assume that we have annual, the interest rate rate, which is computed every year. So I say is R. Okay.
Mhm.
That is every year. So their interest is computing every year. So the interest is R. So R could be like 1/10 or 1/100. Okay. That means 10% or 1%. Okay. So
Okay.
if you deposit like 1,000, say dollar, if you deposit so $1,000, that's the initial money. Okay, so what would be the value of the money after 1 year? So the initial money is 1,000. So the value of your money after 1 year is what? Is 1,000. That's the initial value plus the interest, but the interest is 1,000 times R, the interest rate. So R can be like 1% or whatever, right? So this would be 1,000 times, if you factor out 1,000, you get 1,000 times 1 plus R. Right? Now, what is the money after 2 years?
Mm.
So after 2 years, you have your money after 1 year, which is your 1,000 times 1 plus R, plus the rate, the interest, sorry. The interest, you have to multiply this by R. So plus 1,000 times 1 plus R times R. Now, if you factor out 1,000 times 1 plus R, so from the first you get 1, and from the second you get R. So it would be 1,000 times 1 plus R squared. So that is after 1 year. After 2 years is like this. So what is your money? What do you think after 10 years? Is 1,000 times 1 plus R to the power 10. Does it make sense? Okay. Now, that's just a simple interest that we compute every year. Now, imagine that the bank or the financial institution tells you that they compute the rate monthly. Now look at this. Or computing, sorry, interest monthly. That means you divide your rate by 12, but you compute the interest each month. So what is the value of your money after 1 month? So after 1 month. what you get? So you have your initial money plus 1,000 times R over 12, right? That is 1 over 12, which is 1 month, which is equal to 1,000 times 1 plus R over 12. So I want you to find what you get after 2 months. Let's do it. Let's do it now. Please compute your money after 2 months. So when you want to compute the money after 2 months, you have to look at the money after the first month, and then you multiply it by the interest rate and add it to the money that you have at the beginning of the second month, which is the money after 1 month, okay? So that is your money after 1 month, right? So you multiply this by R and you add to the same number. So this is the number after 1 month, and you have to add the interest. The interest is the same thing times R. Now this would be equal to what? 1,000 times what? Do you agree it's 1 to the power 2?
Yes, agree.
So what is the money after 12 months? If you do the same pattern, to do the same logic, what you get?
1,000 times 1 plus R over 12 to 12 power.
To the power 2. So this is this is called the compound interest, because now you compute the interest monthly. So this is after 1 year, which consists of 12 months. But you remember, if you compute it like normally, after 1 year, you get 1,000 times 1 plus R. But if you compute the compound interest, which is monthly, basically, you get 1,000 times 1 plus R over 12 to the power 12. So I want you to see that these two numbers are different. Which one you think is bigger? So if you compute it like normally, after 1 year, R is the rate of the interest, which is computed every year. You get 1,000 times 1 plus R. So normally you get 1,000 times 1 plus R. But if you compute monthly, you get 1,000 times 1 plus R over 12 to the power 12. Which one you think is bigger?
I think monthly.
Makes sense. It should be bigger if you compute the interest monthly. You can just use your calculator and assume that R is, for instance, 10%, 1 over 10. R is 1 over 10, and compute this. If R is 1 over 10, then after 1 year, what you get if you compute normally? You get 1,000 plus 1,000 times 1 over 10 plus 100. So you get 1,100. How about when you compute it monthly? So let's compare these two numbers. So if you compute yearly, then you have 1000 times 1 plus 1 over 10. Monthly, what you get if you compute it monthly? You get 1000 times 1 over 1 plus 1 over, you have to multiply it by 12 to the power 12. Use your calculator, compute this. 1 plus 1 over 20 to the power 12, and then multiply it with 1000.
That's 1104 point.
Okay. It's like this, right?
Yeah.
Okay. So it's $4 more than normal thing.
Mm.
You see?
Mm.
Okay. Very good. Now imagine instead of monthly, you do it daily,
Wow.
hourly, every second.
No
Use
bank
the
will
same-
give this.
Use the same logic. Yeah. This is your homework. Compute it if the rate is computed daily and then hourly.
Mm.
After 1 year. Okay.
Mm.
Okay, do it right now. So imagine that you want to compute the money after 1 year, but you do compute the interest daily. So first of all, you have to divide R, because every year consists of 365 days, right? So just say that. Sorry. Interest. So you have to divide R by 365. I mean, you can, instead of R, you can just put 10%, but it doesn't matter. It can be anything. By the way, have you seen this before?
No.
Okay. How about others, you guys? Have you seen this before? Okay. Okay, so let's do. Doing the pen. Okay, let me write. So if you compute the interest daily, then what is the money after 1 day? So the money after 1 day would be 1,000 plus the interest, but the interest is 1,000 times R over 365. Now, if you simplify, this would be 1,000 times 1 plus R over 365, right?
Mhm.
Okay. Now, what would be the money after 2 days? So the money after 2 days, you look at the money after 1 day and you add the interest to it, right?
Mhm.
But in order to compute the interest, you just need to multiply it by R over 365. So after 2 days, you get the money after 1 day, which is 1,000 times 1 plus R over 365. And then, yeah, it eventually that would be to the power 2. But if you want to compute it, it's like plus the same thing times R over 360. Now, if you simplify this guy, if you factor out 1,000 times 1 plus R over 365, if you factorize this guy, you get, after 2 days, you get 1,000 times 1 plus R over 365 square. So what would you get after 1 year? It would be 1,000 times 1 plus R over 365 to the power 365, right? Okay, now the question is, if instead of day, you compute hourly or each second, then you would get something like 1,000 times 1 plus R over N to the power N, where N is a very large number, right?
Mhm.
If you want to compute the in terms of hours or seconds or minutes, right? So you have to divide R by N when N is a very large number. And then you have to compute this power. Now, the question is, what is the limit of? So what is the limit of 1 plus R over N to the power N when N goes to infinity? N is a very, very large number. Imagine like computing the interest secondly, every second. Then you get a very large number here for N. And that is equal to, it turns out that this is equal to E to the power R, where E is this irrational Neper number. So the bottom line is that the limit, one way to define the number E is this limit of 1 plus 1 over N to the power N when n goes to infinity is equal to e. Okay, and that is one way to define the number e. So you can make a table and see what this number is. 1 plus, for instance, 1 plus 1 over 100 to the power 100. 1 plus 1 over 1000 to the power 1000. It approaches the number e when n gets bigger and bigger. So let's go back, look at our example. So when you do the computation, the interest, like every second or every minute, then you get, when you, so when we say continuous, so compound continuous interest. So we have 1000 times 1 plus r to the power n when n goes to infinity. That is equal to, but this guy, 1 plus r over n to the power n when n goes to infinity, this guy would be e to the power r. So this would be 1000 times e to the power r. So I want you, what is the number e? So it's 2.71. Imagine that it's 2.7. So I want to compute this. So E is something close to 2.7. Just use your calculator, plug in E equal to 2.7, and R is the interest, like R is 1 over 10. Compute this number. So 1000 times 2.7 to the power 1 over 10. Can you compute this number? 1000 times 2.7 to the power 1 over 10.
I think it's 1104.
0, 4,
Four
point.
point 425.
Okay. So you see the difference here. It's a small difference, but so it's bigger, of course.
Mm.
Okay.
Mm-hmm.
Do you have any questions about these computations that we did
No.
for interest? Okay, guys. So